Hello, we're going to talk about topic 1.10, exploring types of discontinuities. There's two types of discontinuities we're going to take a look at, removable and non-removable. And we're going to try to define them verbally, mathematically, numerically, the works. So we're going to start with removable discontinuities. And ultimately, when you have a removable discontinuity, the limit as you approach a specific value exists. The output doesn't necessarily have to exist, but if it does, then it typically doesn't equal the value of the limit. So we have a discontinuity. I have the first graph over here on the left, and you can tell I'm going to just do some notation underneath it. Let's use some purple here. Okay, so if I take the limit as x approaches a from the left of f of x, that's going to equal L. If I take the limit as x approaches a from the right of f of x, that also equals L. So we can conclude, using our definition for limits here, the limit as x approaches a, the two-sided limit of f of x, is going to be L. However, okay, f of a, if I just want to know the output at that value, that does not exist. And ultimately, because the output is not the value L, we know that there has to be a removable discontinuity. Okay, so the limit for a removable discontinuity exists. And it's going to be some sort of discrete value. However, the output is not necessarily that value. So if you take a look at the second graph here, we have a slightly different thing. So for the same reason, we can say that the limit as x approaches a does exist. And from the left and from the right, we're still approaching the value of L. However, f of a is going to equal to the value of m. And because these two things are not equal, we know there's a removable discontinuity. All right, so that's how we can tell mathematically and visually how we know that there's going to be a removable discontinuity in our function. Okay, now I have two algebraic representations here. I want to talk about what it looks like to be a removable discontinuity in this sense. We'll take a look at them. We'll even try to maybe graph them a little bit. But for this first one, when you have a rational function, okay, so we can always identify a removable discontinuity if you can simplify an expression of x, right? So if I can simplify out an expression of x, that expression is going to tell me the location of a removable discontinuity. Ultimately, I can remove it from my function. So if I do this, I have a difference of squares in the numerator. So I have x minus a, x plus a, all over an x minus a. And those x minus a's reduce. So I have now f of x. Well, I guess I don't really want to necessarily use f of x here. But I know that I can reduce this to x plus a all over 1, so I don't really need the x plus a. Now, here's the part where I need you to understand, is the piece that was removed, so my removable discontinuity is going to be when that piece that reduced is equal to 0. So you can always set that equal to 0 and solve it. And if you solve it, I think we can all understand that we're going to get when x is a. So more importantly, is a removable discontinuity is a point. So every point has an x and a y value, right? So if I want to take that x value, I can find the y value of that whole, and I can substitute it into the simplified expression, or I like to call it the extended function, right? So if I take the a value and I substitute it in, I would get a plus a, which gives me a y value of 2a, okay? And my removable discontinuity would be at this coordinate, Okay. Now with a piecewise function, we can still identify if there's a removable discontinuity. So again, the first one was rational. Anytime you can reduce an expression of x, typically you have a removable discontinuity. For a piecewise function, we can still identify if there's a removable discontinuity because I'm going to see, okay, the limit as x approaches 0 from the left of f of x is going to be the sine function. So that's going to be the sine of 0. And if you guys remember, sine of 0 is 0. I can say the limit as x approaches 0 from the right of f of x is going to be the quadratic, so 0 squared, which is still 0. So we know that the limit as x approaches 0, the two-sided limit, is going to be 0. However, you can see in the middle of our piecewise function, we know f of 0 is 1. And because the big statement here is the limit as x approaches 0 of f of x does not equal f of 0. And because those two things aren't equal, we know that there's a removable discontinuity. Just to give you a visual of what's going on here, we can even draw a little graph. Sine of x less than 0, looks something like this. Again, not defined there. And then I have x squared greater than 0 is a quadratic piece. And then at 0, I'm going to be at a value of 1. Okay. And actually, there's a typo here. This should be just greater. That should not be equal to, because again, in order to be a function, we can't really have it defined at two different points. Okay, so we would have something like that looks like this. Okay, so that's where we would get it. All right, but you can see visually the limit from the left is equal to the limit from the right, and then the output's something different. That's a removable discontinuity. All right. So we also have non-removable discontinuities, and there's two types that we're going to really focus on. The first one is called a jump discontinuity, and ultimately you can see kind of the visual underneath. It's when the limit from the left is not going to be equal to the limit from the right. So as the graph approaches one value from the left side, it's not going to necessarily approach the same value from the right side. They're not going to match up. So if you take a look at my first one, again, using some math notation here, if you ever need to explain, the limit as x approaches a from the left, we're going to call this function f of x, even though it's not labeled, is L. And the limit as x approaches a from the right of f of x is going to be m. Because those two things are going to two different y values, we know that there's a jump discontinuity. Okay. Now, before I graph it, I can still show the same thing for the second one. The limit as x approaches 1 from the left of f of x. Okay, if I approach 1, I'm going to substitute 1 into my first piece of my piecewise. And if you do that, I get 0. The limit as x approaches 1 from the right of f of x, if I plug into the right side of my equation, so 2 to the first minus 4 is going to be a negative 2. So those two things obviously are not equal. We know that there's a jump discontinuity at 1. They're going to two different values. Now visually, we can see what that looks like. So if I do the left side in blue here, so at 1, we know that it was at 0, and it's going to be an open circle. And it's radical, and if I plug in 0, I'm going to get 1. If I plug in negative 3, I'm going to get 2. So I get a kind of a radical function that looks like this. And then I have an exponential function. If I plug in 1, we would know we're at negative 2. And I can make that a closed circle. If I plug in 2, I'm at 0. If I plug in 3, I'm at 4. So I get something that looks like this. So you can see that from the left side, it goes to the hole. From the right side, it goes to the point beneath the hole. Because those go to two different values, then I know that there's got to be a jump discontinuity. Okay. Now down here, if you want to, I'm going to pass by this, but you can create your own piecewise function, and actually it's probably easier to create a piecewise function where there is a jump than to create one where there's not. But if you have any questions about this, please ask. Step function. Okay, so I have here a step function has an infinite number of jump discontinuities, right? It's just a constant piece to a different constant piece to a different constant piece. And ultimately, this is a floor function which just rounds every decimal down, right? So any real number between 0 and 1 is just going to get rounded down to 0. Any real number between 1 and 2 is going to get rounded down to 1. So you can kind of see how this graph operates. Now, if you can tell, there is a jump discontinuity at every integer, okay? So at 1, at 2, at 3, at 4, at -1, at -2, and so on and so forth. Now, you have to also understand that my window goes way beyond 4. So to really say that, okay, well, all the integers, 1, 2, 3, 4, and -1, 2, 3, 4, that's not really describing all the jump discontinuities. So I just want you to be aware of how to write this. So I'm going to say that there are jump discontinuities and I'm going to just create a dummy variable. I'm going to say at x equals a, and I'm going to put a disclaimer where a is any integer, right? So all my jump discontinuities are going to be at any integer, and this is how I would notate it. So you can create a variable, but then you have to define what that variable is right after it, okay? So this is a way that you can do that. Let's keep going to the next type of non-removable discontinuities. So these are types of discontinuities you cannot simplify out of your problem. And we have infinite discontinuities. And ultimately, you probably know them as asymptotes, right? Vertical asymptotes. And you have a infinite discontinuity if you approach a value, an x value, from the left or from the right. And it's or, right? So if one or the other happens, then we know that there's an infinite discontinuity. If either of those limits go to infinity or negative infinity, right, then we know we have an infinite discontinuity. So here are two examples here. Ultimately, the limit as x approaches a from the left of my function is going to go to infinity. Now I could stop there. I don't really have to prove the right side. As long as one of the sides goes to infinity, I know there's an infinite discontinuity. But we do, in this case, we do have both. So if you just proved one, that's enough evidence. But I can do the right side, and the right side goes to negative infinity. Clearly, that limit doesn't exist. If the limit doesn't exist, it can't be continuous. So on the second graph, the limit as x approaches a from the left of f of x goes to negative infinity. The limit as x approaches a from the right of f of x also goes to negative infinity. And because one of them, and in this case, both of them go to negative infinity, we know there's an infinite discontinuity. So I have two algebraic representations here. So 1 over x squared. I don't know if you guys did your little summer packets, so you might know what 1 over x squared looks like. Let's get my pen here. So it looks a little something like this, right? And if you look at that graph, ultimately, and if you look at the equation for that matter, the equation is going to be undefined when the denominator is 0, right? So when x equals 0 is going to be a discontinuity, right? It's going to be a vertical asymptote. But you can visually see it, the limit as x approaches 0 from the left of f of x equals infinity, and the limit as x approaches 0 from the right of f of x also equals infinity. All right, so we have an infinite discontinuity. Now, tangent's a little bit more interesting. I'm going to write tangent as the sine of x over cosine of x. We all know it as. And if you remember what the tangent graph looks like, I'm not going to scale it. I'm just going to draw a quick sketch here. But we have all of these vertical asymptotes. Now, if I wanted you to tell me where all of the infinite discontinuities are on a tangent graph, there are an infinite number of them, right? So ultimately, we need to take a look at when this cosine is going to be 0. So I'm going to put it over here. I want to know when cosine of x is 0. And cosine of x is 0 at pi halves, at 3 pi halves, and so on. So, and there's an infinite number of these. So what I'm going to do is I'm going to say pi halves plus, and I'm going to create that dummy variable. I'm going to use a k pi. So if I do pi halves plus a multiple of pi, then that will give me all of the locations of a asymptote, vertical asymptote. Now, I do need to still, because I created a dummy variable, where k is any integer. So if you create a variable, you can't just create one and walk away from it. You have to define what it is. No one's going to make that assumption that it's going to be an integer. Because it could be a real number, it could be decimal fraction. So we need to define exactly what it is we're talking about. K is an integer, positive or negative, right? All right. So next piece. So there's an example, all right? So feel free to pause, and you're welcome to try to do this on your own. I'm going to kind of run through it real quick. But I'm going to take a look at this graph. I'm going to determine if the discontinuity is removable, jump, or infinite. And then I'm going to try to justify it using limits of why it is that type of discontinuity. So at -2, right, you can see that there's a hole here. So that's going to be a removable discontinuity. And if I want a mathematical justification, I can say that the limit as x approaches -2, the two-sided limit does exist. It's 2. However, I don't want to use a limit. However, f of -2 does not exist. Therefore, if I wrote a sentence, then I could use my little therefore symbol. Therefore, you know that there's a removable discontinuity because the limit does not equal the output, right? So at 0.5, and actually there's a typo here. So if you're following along, this should be a negative 0.5. If I do this, this is also, so I'm talking about this value right here. This is also a removable discontinuity. And the reason being is because the limit as x approaches a negative 0.5 of f of x is going to be equal to, I'm going to go up here. Now I'm going to approximate. So we don't really know where that is, right? They didn't give us an equation. So I'm afraid to use a value. So the best thing I can say is that it's just not going to be equal to f of negative 0.5, right? So we know that those two things are not going to be equal. I don't really have enough information to say where the hole is, and I don't really want to estimate it. However, I do know that those two things are not equal. Therefore, there's a removable discontinuity. All right. So keep going. At 0 is the next problem. So if you look at 0, now in this case, from the left, I go to 3, and from the right, I go from 5. So that's going to be a jump discontinuity, and I'm going to be specific here. I'm going to start by calling it a non-removable discontinuity. And then you can be more specific of what type of non-removable to jump, right? Jump discontinuity. And the reason being is because the limit as x approaches 0 from the left of f of x does not equal the limit as x approaches the right of f of x. And you could probably, if my box is a little bigger, you can even be more specific on what those values are. I could say the limit from the left is 3, the limit from the right is 5. Therefore, those two limits don't exist. You know you have a jump discontinuity. Okay? So next one is at 1. So if you look 1 from the left, I'm at 4. 1 from the right, I'm at 0. So again, same reasoning. I have a non-removable discontinuity. And it's going to be a jump. So, and the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right of f of x. Therefore, we know it's a jump. Okay, so I think I have 2 more. So at 3, okay, so if you look from the left here, this is going up, okay, and this will keep going up. It won't cross that vertical line. That's what that dashed line is meant to represent. So I can say here we have another non-removable and this is infinite. And if I take the limit as x approaches 3 from the left of f of x, we know that that's going to infinity. Now, you can also say the right side is probably going to negative infinity. But again, if you need to define an infinite discontinuity, you just have to prove either the left or the right are going to infinity or negative infinity, and that's enough evidence. Okay. Last one is number 5. Oops. On number 5, or x equals 5, I have this point here. In this case, the limit does exist. All right. However, the output does not. So the limit will go to the y value of 5. So we can write that down. So I have a removable discontinuity. And I know that the limit as x approaches 5 does exist. And it gave us 5. However, f of 5 does not exist. And because those two things don't give us the same value, we know there's a removable discontinuity. Okay. So now I have 2 functions here. So we're going to do this algebraically, and I think that's going to be the end of our notes. So I just want to show that we have removable discontinuities or non-removable discontinuities in these problems. So I'm going to start by factoring. So I have 3. I'm going to x plus 2. If I factor the denominator, I have x minus 7, x plus 2. Again, the x plus 2's cancel. So now I know I have a removable discontinuity at -2. Now I'll find the y value in a minute. But when I reduce that, I have a 3 over x minus 7. Now you might notice a little change in notation that I did here. I didn't necessarily say use an equal sign. I used a little arrow because I don't want to say that those two functions are equal anymore because one has a whole and one doesn't any, So I just use an arrow to say I simplified it, but they're not technically equal anymore. And then I have, you can see from my reduced form, I have a non-removable discontinuity and it's going to be an asymptote, so all asymptotes are an equation of a line at x equals 7. Okay, so the only thing I have to do now is I'm curious to know what the y value of this whole is. So if you were to take -2 and you substitute it in, I can say 3 over a -2 minus 7. And if you reduce this, you'll get a -2 comma 3 over -9, which is a -1/3. Okay, so that would be the location of my hole. All right, so I had two discontinuities. Also, you can say this non-removable, because it's an asymptote, is going to be infinite. All right. Next, I have a piecewise function, right? So now here's something that's important. The top function is a quadratic, right? So quadratics are continuous at all their values. The second function is also quadratic, so we know that's continuous at all its values. So we don't really have to worry about discontinuities within each piece, but we do need to know whether or not these two pieces are going to actually match up, if they're going to actually connect. So what I want to do is I want to take the limit as x approaches 2 from the left of f of x is going to be 3 times 2 squared minus 2 plus 5. And if I do that, what do I get here? I get 12 minus 2 plus 5, and I get 5. And then if I do the limit as x approaches 2 from the right of f of x, then I get 4 plus 7 times 2 minus 2 squared. And if I reduce that, I get 4 plus 14 minus 4. So that's convenient. I just get a 14. So ultimately, you can see that these two values are not the same. So because I have the limit as x approaches 2 from the left of f of x, that does not equal the limit as x approaches 2 from the right of f of x, then I know there is a non-removable discontinuity at x equals 2. And more importantly, you even know that it's a jump discontinuity. Okay? Hopefully these notes helped. If you have any questions, please let me know. Feel free to rewind, pause, fast forward, whatever you need to do. And have a good day.